So, hello, welcome to Apache Kafka 101. My name is Hugh. I am a senior developer advocate at Aiven, where I help to look after our Kafka community. Today, we're going to be looking at Apache Kafka, what Apache Kafka is, the circumstances in which you want to use it, what it's good at, what it's not so good at. We're going to be looking at the basics of Apache Kafka, what are the key concepts that you need to understand to use Kafka at work or in personal projects or elsewhere. We're going to be walking through a step-by-step tutorial of how to create your first Kafka cluster and to produce and consume messages from it using the Aiven platform. And then we're going to talk about some next steps on your Kafka learning journey. If you haven't already, I would strongly encourage you to go and check out the materials for this session. We're going to have a little bit of some slides up front talking about what Kafka is and how it works, but then we're going to walk through a practical session. So do check out the link in the comments for how to get started with that. I would recommend moving on to the point where you create your code base and then we can pick up from there together. Just whilst you're having a look at that, a brief note on who Aiven are and what we do. Aiven are a managed open source data services company. So we take awesome open source projects like Apache Kafka, ClickHouse, Postgres, Valkey, OpenSearch, and so on. And we provide them as managed services for our users. This means that you get all of the benefits of using open source technologies, which is strong community support, innovation, avoiding vendor lock-in, having the code available to you to do security analysis without the complexity of having to own and operate an open source project from first principles. We have a very kind of multi-layered practice as a company. So we offer our managed services on all of the major cloud providers, including AWS, GCP, and Azure. And we typically handle all of the things that a DevOps team often would. So we're thinking about things like backups, maintenance, upgrades, and migration. So you can focus on just building stuff. As I said, we offer a variety of different data services, but increasingly we are offering support for broader kind of governance and AI use cases. That's coming in the form of increased support for continuous data capture, context storage, and other tooling. We are very much a production-ready platform, an AI-ready platform. We now have lots of MCP stuff for connecting to agents. We support Terraform, Kubernetes, all of the ways that you may want to manage your infrastructure in prod. But that is enough about Aiven. Let's talk about Apache Kafka. So what actually is Kafka? So Kafka is an event streaming technology that was made open source by LinkedIn back in 2011. They had a problem where, building their software stack for their very popular, or popular at the time, business kind of social network website is that they had a very large number of events in the shape of event data. You can think of an event as any kind of measurement or set of measurements or fields associated with a particular time. So think, changing temperature readings from a thermostat, errors from a running application, communication between microservices. And in order to handle that volume of events, LinkedIn built and then subsequently open sourced their own solution, which is Apache Kafka. As a distributed event streaming platform, Kafka provides the ability for you to produce messages to a cluster and then consume them to do stuff with them later on. Whilst those messages are in the cluster, they are stored in logical groups called topics. So you might have a topic like temperature, transaction data, order data, handling different things and storing messages with those data. The topics themselves are then written and stored as partitions. So when a message is produced, it's written to the end of a relevant partition, because Kafka, as opposed to some other event streaming technologies, which use more of a queue model or a stack model where a message is written to the streaming layer, and then it's read, and then it's removed from the layer. Kafka uses a distributed log, where messages are added to the end of the log, and they are kept for a retention period, and messages are read from an offset. More on that in a moment. Very common use cases of Apache Kafka are things like microservices architectures, allowing microservices to communicate, IoT, everything from industrial sensors in factories to F1 cars, produce data to Kafka, and then see it consumed later on for analytics. And deployments like continuous data capture, where the set of changes and operations applied to one database are copied and repeated on another for the purposes of migration or replication for the purposes of durability. So why use Apache Kafka? Why have this event streaming layer between your producers and consumers of data? Firstly, as I mentioned with LinkedIn, the initial motivation for creating Kafka is dealing with applications at scale. It can cope with a very large volume of events whilst having very little downtime, which comes on to the second strong suit of Kafka, which is durability. Because you have a horizontally replicated data set, you can lose the individual brokers that make up a cluster, the actual servers that are running the pieces of Kafka, without data loss, because you have multiple copies across multiple brokers. Again, because Kafka uses this distributed log model rather than a queue where when a message reaches the front, it's removed from the cluster, messages are retained for a retention period, which means if you have disruption of the downstream consumers, you can resolve whatever issue is going on there and then replay messages from the start of the log to resolve any issues you may be having. Kafka, as an open source project and as a project which has existed now for more than 15 years, has a very high degree of support, especially from other Apache Software Foundation projects. So it's extremely easy to connect Kafka to different technologies. If you're working with databases for CDC, if you're working with observability tooling, if you're working with OTel, if you are working with IoT, if you're working with web stream data with clicks, it's extremely likely that there will be a first-class plugin, connector, or support for directly streaming your data to Kafka and consuming it from Kafka. So Kafka is this kind of Swiss Army knife that allows you to glue all the different parts of your architecture together without having to maintain lots of different connectors. Finally, last but not least, Apache Kafka is very good at working with real-time data, which is to say, you can have a message produced to Kafka, consumed, and being used by a downstream service, whether it's written into a DB or being processed by a microservice, in less than a second if it's configured correctly, which means it can support all manner of low latency applications. So if you have an agent consuming data and making decisions, if you have a predictive model, if you have alerting, Kafka is a great choice. So let's talk about some of the basics of Kafka, the fundamentals you need to understand to make sense of it as a technology. So when a message is produced to Kafka, it is produced to a topic. A topic is a kind of a logical separation of data in Kafka. It's a name for a group of events that are stored as partitions. The process of producing data to Kafka consists of taking the data you want to write. So that's usually a time and some fields. So for IoT, you can think you might have temperature or pressure data, for example. You might have financial data for transactions if you have some kind of web app microservice with dollar amounts, user accounts, IDs, and things like that. So you'll have those as fields and you'll have a time. That is then serialized into the data storage format that Kafka uses under the hood and written to the offset. The offset in an Apache Kafka topic is just the end of the data that has already been written. And when your data is consumed, it is consumed from the last offset data was read from. So it's very much like a queue. But again, the important aspect here is that data is not removed or deleted once it's read. It remains in place. All that changes is data being read to the end of that offset and the position of the consumer offset. If you have any issues downstream, you can reset your consumer offset back to the start and replay messages, which is very useful. Before I was a developer advocate at Aiven, I was a consultant working with retailers in the UK. We used to set our Kafka data retention to 3 days. So that means that from the time you write your data to your Apache Kafka topic to the time it is automatically deleted is 3 days. Storing data forever would get very expensive. But by storing data for 3 days, it meant that if there was an issue over the weekend, we could just replay data from the beginning. And it meant that people didn't have to be on call over the weekend. So that's one of the strengths of Kafka, is that durability, right? And it can be very useful in practice, both in terms of the things that companies and businesses need out of their data architectures, but also things that we need as engineers. It can save you some sleep, which is pretty terrific. The next thing that you need to understand, other than topics and offsets about Kafka, is partitions and replication of partitions. As I mentioned before, a Kafka cluster is made up of multiple brokers. This serves two main purposes. The first is durability, which we've already discussed, and the second is throughput. When a message is produced to Kafka, when it is written to your offset at the end of your topic, it is produced to a particular broker. So that is the leader broker for that topic. That leader broker has a number of responsibilities, primarily maintaining the ordering of the Kafka messages to make sure they arrive in the same order at the consumer as they were produced. The leader broker receives those messages and then writes them to a partition, which is a file that makes up some portion of the topic, to the local disk. It is then replicated to follower brokers throughout the rest of the cluster. This is great for durability, but it's great for throughput because it means when you come to consume the message, you can get it from any one of the brokers in the cluster. So you have effectively 3 times the bandwidth consumption of messages as you do for production. It is worth noting also the leader broker for one topic is not leader broker for another topic. So the responsibility and the extra work associated with preserving the ordering of messages and of receiving the requests from the other brokers for partition data is shared equally across all of the clusters, assuming there's a roughly evenly divisible number of topics. The amount of times that the partition is replicated, that is the number of copies of it that are made across brokers, is configured by the replication factor. In a typical enterprise Kafka cluster, you might expect to see 3 brokers with a replication factor of 3, which means that each partition has 3 copies across each broker, which means that you can lose one broker and still have 2 copies. Finally, a really important concept to understand when using Apache Kafka is consumer groups. Kafka, by default, preserves strict ordering. So the messages are consumed in the same order that they are produced. But depending on what you're doing with those messages, you might need some more guarantees than that. For example, if you have a microservices architecture, it's likely that you're going to scale horizontally, which is to say that you're going to have multiple copies of whatever application or technology is consuming from Kafka. You might want to guarantee that messages are only processed once. For example, in the case of transactions, if your Kafka topic contains information about some payment that needs to be made, you don't want to make that payment twice, or you don't want to bill someone's card twice. So something that can be done to help ensure messages are only processed once is using consumer groups. A consumer group is a logical collection of consumers, and it guarantees that for every message in a topic that's consumed, it's guaranteed to be consumed in order, but it's guaranteed to be consumed by only one consumer in that group. So that helps avoid the problem of double consumption. If you have a topic on a broker with 2 consumers reading from it without a consumer group, their consumer offset may be different or maybe the same, which can cause them to process the same message multiple times. So a consumer group is a very useful thing if you have a parallelized or a horizontally scaled downstream consuming from Kafka. Okay, so we touched on some Kafka basics. We've spoken about brokers, topics, offsets, partitions, and consumer groups, as well as some of what happens during the produce and consume process. Now we're going to take a look at putting that into practice. If you haven't already, I would encourage you to jump over to the repo that we're going to be walking through together and head to the Get Started page and create a GitHub code space with the session materials in them. I already have a code space started here, so I'm just going to restart that. Thank you, Tibbs. Just going to give this a second to get started. Let me know if you can see that okay. Need this agent view. Cool. Very nearly there. Excellent. So to get started, we need to download the Python packages that we need to interact with Kafka from these Python notebooks that we'll be using. If you are using GitHub Codespaces, they should have been downloaded automatically, so you can skip this step. Next up, we are going to create a Kafka cluster. At Aiven, we are proud to provide a number of the open source services that we host completely for free for the purposes of learning or building personal projects, which includes Apache Kafka. If you take a look at part 2 of the setup notebook, you will see that there is this link to sign up to Aiven and create your Apache Kafka service. Totally free, you don't need a credit card or anything, and there are steps for deleting this Aiven account if you don't want it at the end of the session. So I would encourage you to head over there and create your service. Once you've done that, you should see something that looks a little bit like this. So you can see here, I have an Apache Kafka 4.2.1 service run here in the Aiven console. And it is a free tier deployment. So it's pretty free to use. I believe it supports 250 kilobytes a second of traffic. It has 2 brokers, so a replication factor of 2, and it supports 5 topics. If you need more than that later on, you can always upgrade. In order to produce and consume from our Kafka cluster, we need our certificates to encrypt and decrypt the messages. You can find them here from the Apache Kafka view in the console. You'll see that there is this client certificate option. If you click that, we can then download our access key, our access certificate, and our CA certificate. Please, what pros and cons does Kafka have over other services like Python, PopulaDB, SQL Alchemy? That is a really good question. I'm going to follow up with that after the workshop because we'll have to get into some of the pros and cons of message brokering on databases versus direct streaming, but that's a great question. Once you've downloaded your certificates, you want to go to the SSL certs directory in your code space. Just going to right click here and I am going to upload files. I'm going to upload all of the certs I've just downloaded. I'm going to need to tidy these up a little bit because I already had some certificates installed. So I'm just going to get rid of the ones from my file names. Not too worried about you seeing these certificates either because they are for a throwaway cluster. And then we are going to copy the service URI into an environment file. So I'm just going to create a, I'm going to right click in my going to right click in my GitHub code space, create a new file called .env, and then copying the, in fact, I have a command here to do exactly that, so I don't need to create a new file. I'm going to go to setup, and I'm going to replace this string with my URI from the console. So your URI is up here in your Kafka cluster view, and that contains the URL to where your cluster can be found on Aiven and the port, which is open for producers and consumers. I'm going to paste that into this cell in the notebook here, and I'm going to run it. Use my Python environment, use this existing environment, which was created when we ran the code space. I'm just going to wait a second for this to catch up. And we can see now that we have this environment file with our environment variable for the Kafka service URI that we use in the next step. So you should now have a Apache Kafka cluster. You should have all of your certificates downloaded from that cluster and copied into SSL certs, and you should have an environment file with your URI. And give everyone a second to catch up and get that done. Give me a wave in the chat when you're ready. In the meantime, Patrick, your question about the pros and cons does Kafka have over SQL Alchemy? So a database like SQL Alchemy is what's called a transactional database. So it's designed for the efficient writing and processing of tabular data, namely with a form of rows. It's designed to be efficient for things like writing, changing particular rows, and aggregating, as opposed to an OLAP database, which is designed to be more efficient for aggregating columnar data. For low volumes of traffic, making transactions and changing a database like SQL Alchemy is very quick, it's very efficient. But you will start to have problems if you're making changes very quickly. There's some really good analysis out there from a blog called 2 Minute Streaming, written by the lovely Stan, where he makes a comparison, not in the case of SQL Alchemy, but with Postgres, where you can do pub/sub, so you can do Kafka-like stuff against an OLTP database, and it works, and it sort of competes with Kafka up to a certain volume of messages, which is, I believe, something like a megabyte a second or something like that, and at which point it just can't keep up. Kafka is designed to be performant for that kind of data, and OLTP databases are not. So that's the main trade-off. Yes, there you go. Nice work, Tibbs, on sharing that. There are other examples also in the sense that Kafka is designed for working with streaming data, and it fits into this ecosystem for events and for event tooling. You will find that certainly for OLTP. So there are some great tools that you can put on top of an OLTP database that will make it behave like a streaming tool, but it's not necessarily first party or native. So because Kafka has been around for so long and so widely used, you'll likely find better support for doing streaming things. So it really depends on what you're trying to do. SQL Alchemy will likely be simpler and cheaper for smaller data volumes, but for larger data volumes, you're going to run into issues. But yeah, fantastic question. I can see a few people in the chat saying ready. So let's move on to the next section, producing messages with Python. So in this notebook, we can see that we have this example around producing a message about pizza to our Kafka topic. So if we scroll down in here, we can see we have this example. So we are going to authenticate using the Confluent Kafka Python library, and we're going to build this object that contains our service URI, which again is the URL and the port. We're going to set a client ID. This is something which is used for logging on the Kafka cluster size. So your client ID would probably be set to something like the name of the application that is producing or consuming data. And then we have all three of the secret files that we've downloaded, which are used for encrypting and decrypting data from Kafka. Next up, we're going to create a topic. We have this little helper function here that's just going to check and see if a topic exists. And if it has pre-existing partitions, and if it doesn't, we're going to create a new topic. In this case, we're going to create a topic called pizzas. And then we are going to configure our producer. So the way that this client, this Python client for Kafka works is that you have a object for the producer and an object for the consumer. And then you can initialize them, and then it will wrap any subsequent produce and consume operations. So we're going to initialize a producer object based on the producer class with all of our information from up here. And then we can just use the produce method to send a message to our topic, to produce a message. So I think I may have already run this, but if I run this now, okay, here we go. I'm going to set my kernel. I'm going to run this. And we can see we've created a new topic called pizzas, and we have sent our order. So we have ordered for my colleague Francesco 1 margarita pizza. If I jump back over to the Aiven console and I come over to topics, you can see that we have a pizzas topic with 1 partition and a replication factor of 2. And so we have 1 partition that has that 1 message in it, and we have 2 copies of it. And if I jump over to pizzas, we can view the messages if we enable Apache Kafka REST. So Apache Kafka REST is just a REST API for your Kafka service. So you can both produce and consume to Kafka using a Kafka client, but you can also use API methods against it to read and write data, which is what the console uses. So now if I come to our pizzas topic with REST enabled, I can review messages, review my messages, I can fetch messages, and there we go. And so you can see that we have this message in our topic, but it's kind of gibberish at the minute. That's because it's base 64 encoded. Your data, when you produce it to Kafka, gets serialized for more efficient storage and processing. And so as we're reading it here in flight between producer and consumer, we need to deserialize it in order to make sense of it. But we can see that we have produced our message with the key of 1, which is the current offset with Francesco's pizza order. So we jump back to code spaces. We can see now that we can reuse this approach to send some other pizza orders. Have a go at adding yourself here. See if you can order yourself your favorite pizza. I am going to do that now. So we have these 2 orders here, 1 for Adele and 1 for Jay. Jay is my colleague in DevRel. I'm going to change his pizza order to another Hawaiian, if I can spell. And then I'm going to add a pizza order for me. So I'm creating my schema here where I have my name field, and then I'm going to put in my name. I'm going to add my pizza field. And I want caprese pizza. And then need a trailing comma. So now I can reuse the same method we used before of producer produce, and I can iterate over this array of orders. I can send 3 orders. And then if I come back to topics, I can fetch messages, and I can see that I now have 4 messages in my Kafka topic. And so we've produced our pizza orders to Kafka, which is all well and good. In order to do anything with them, we need to consume those messages back. And in order to do that, we're going to use the same approach. So again, we're going to create a configuration object with all of the details we need to authenticate with Kafka. But this time for the consumer, we have a few more fields which we didn't have for the producer. Notice that this time we have an offset. This is because the offset that the producer and the consumer use are separate. The producer currently is configured to write to the offset at the end of the topic, But our consumer needs to know where it should start consuming from. In this case, we're going to tell it to start consuming from the earliest. So each time we use our consumer to consume, we will begin from the start of the topic and read messages back. We are also specifying our group ID. So we have our group ID of pizza early, and any consumers with this group ID will consume each message uniquely between them. So if I have two pizza early consumers, they each consume pizzas uniquely. And then again, we have our client ID, which is just useful for specifying what app is doing things for logging purposes. And we're going to initialize our consumer object. Again, I'm just going to pick the kernel from the notebook and run that. Cool. So now we're going to create this console object, which will allow us to view messages live as they come in. And we're going to start our consumer. This code will allow us to view messages as they arrive in our Kafka topic, and it'll print them out to the shell. So what we're going to do is we're going to run this code, which will consume and read messages and show us what's coming in. And then we can go back to our previous example, produce messages, and watch them arrive in real time. So let's try that now. Cool. So we're going back to produce one, and we're going to run our orders again. We've sent 3 orders. If we come back to consume, we can see in our console, each of our orders has arrived. Now we can see with Python, very simply produce and consume orders. Obviously, we're just doing this locally with 2 Python notebooks on the same machine. But I hope you can see how this Python code can be run in 2 different places, whether it's an EC2 instance or a Lambda function or a runtime for your microservices, or even a connector to some other technology to produce and consume messages. So those are the most fundamental things you need to understand to interact with Kafka are your producer configuration and your consumer configuration. Let's take a look now at topic partitions. The configuration of topic partitions is one of the most important aspects of the performance of a Kafka cluster. Generally speaking, you want to have roughly an equivalent number of partitions to the number of producers and consumers that you have. If you have one partition at any given time, because that partition is one file, only one producer or consumer can be reading and writing to it at the same time. Equally, you do not want to have a very large number of partitions, because your consumers and producers will have to be continuously opening different partitions, opening different files and reading and writing to them in order to complete the process of producing and consuming, which again adds time latency to what should be a very low latency operation. So as a result, you want to make sure that you are matching your number of partitions to your number of producers and consumers. In this example, up until now, we've only had one producer and one consumer. So one partition is fine. We have a replication factor of 2 because we have a 2 broker cluster on free tier, which means we have 2 copies. So we have a little bit of resilience there, but 3 copies would be better. But if we want to add another consumer, we need to add another partition to our topic. The issue with partition configuration for Kafka is that it is not easy to change the number of partitions once you have set it. The ideal time to set the number of partitions for a topic is at creation time, and you generally speaking want to avoid changing later on. The reason for this is, as we discussed before, each of your partitions is on a different broker. If you want to change your number of partitions, you need to copy and move that data around the brokers to redistribute it in the way that you want. So changing replication factor, changing number of partitions has a cost. And that process is called rebalancing. And it can be quite expensive in terms of time and also money if you are paying heavily for network meterage. We will have more on some different approaches to mitigating that cost in future sessions about diskless Kafka. So keep an eye out if you're interested. But for now, we're going to create another instance of the producer class. And this time, we're going to explicitly create a topic with 2 partitions. So we're using the exact same methodology we used before, but this time we are specifying the number of partitions as 2. So if I run this again, I'm going to select the same runtime. You can see that we have created a new topic in our Kafka cluster called pizzas partitioned with 2 partitions. So we are going to produce some pizza orders again to the same topic. So you can see we have our producers produce and our producers flush method. We're going to send an order for Francesco and an order for Adele. Now, if we jump back to the console and we look at our topics, we can see that we now have 2 topics, and we have our new pizzas partition topic, and which has 2 partitions. And we can see, look, we have just produced 2 messages, and they have been evenly split across both partitions. By default, the partitioning strategy in Kafka splits messages by their key, which in this case is just an offset, which is incrementing, and it does it evenly. Depending on what kind of data you're sending, you might mess with this to get better performance out. You can partition by message size, you can partition by age, you can do all kinds of fancy stuff with tiered storage, where once data has been around for a certain time, it stores somewhere different to fresh data. But for now, we're just evenly splitting our data into different partitions, which creates a very balanced cluster, which will give us optimal produce and consume times, particularly given that all of our messages are about the same size and contain the same data. So now that we have produced data to our topic and we have 2 partitions, each with a message, let's have a look at how consuming differs. So we're again going to create a consumer, and we're going to consume from our topic. By default, if I consumed from my topic and I said consume from earliest offset, my consumer would go, here is 2 messages. And I would get the exact same data as we got before. But I can also configure my consumer to consume from a specific partition, which is what I'm going to do now. So we create a consumer object the exact same way we did before. We're going to use earliest offset the exact same way we did before. But this time, when we consume, we're going to consume from a specific partition instead of just consuming from the topic as a whole. And that is assigned at a consumer basis rather than a specific consume operation. So I'm going to run. Oh, what's going on here? Oh, no, there we go. Cool. I've run my consumers, and I can see I have these 2 different consumers. These 2 different responses. So here in our example, we have a different partition per pizza store, and we are partitioning by the ID, which is our store ID. And we can see that for one consumer, we only get messages from one file, and from the other, we only get them from the other partition file. If I come back to the produced partition, I can produce again. So if I produce a pizza order for me and one for my colleague Jay, and run that, and then we rerun our consumers, we'll see that we now have a fresh message in each partition overwriting those IDs at the same offset. Excellent stuff. So we're very nearly there in terms of looking at all of the concepts that we need for understanding the basics of Kafka. The very last is consumer groups. So we have previously been passing our group ID value, which is how we specify our consumer group. And up until now, we've had the same group ID for all of our consumers, because we've just had our consumer, which is the store consuming pizza orders. If we want to do 2 different things with that order information, we probably want 2 different consumer processes, and we might want copies of those processes. So those copies should go into consumer groups, so we're not doing things with those orders multiple times. We're going to create now a consumer for each of our stores, one for North and one for South, with a distinct consumer group ID. Again, I'm going to run that with my Python kernel. And we're going to consume messages from the pizzas partitioned topic. And again, we're going to spit out what we have from the northern store and the southern store. You see we have our results. And then, oh, this is very blue. And then we have our other consumer over here. If I highlight that, you can see it better. So we have our checking consumers, which are in our first consumer group, and we have our billing consumers, which are in our second billing group. And we can see that each consumer has a unique message and has it a single time. So the consumers don't get repeat messages, and all the consumers in the consumer group consume all of the messages without repetition. So there we go. We have just done a very whistle-stop tour of all of the basics of Apache Kafka. Feel free to go back and play with these notebooks and to see what you can do with the code examples, and have a think about how you could apply these principles and these techniques to the different data that you may be working with in your work. When you're done, you can come to the Clean Up Your Services section, which will talk you through deleting your free-tier Apache Kafka cluster and cleaning up the other stuff we've used here. You don't strictly need to delete your cluster. It will automatically be powered off after a certain time of not producing messages to it. But deleting the cluster lets us make sure we have plenty of other free tier services available for other people. So when you're done, that would be awesome. That is a wrap on the tutorial section. If anybody has anything they're stuck on or they have any questions, please do drop a message in the chat. I just want to quickly touch on next steps. These are some resources that I would thoroughly recommend in terms of your onward Kafka learning journey. A very common pattern for working with Kafka data is stream processing. So we've looked at how we can do a simple produce and consume from a Kafka topic, but there's far more you can do with that. You can do transformations, you can change data in place, you can filter data. My colleague Tibbs has a fantastic blog over on the Apache Kafka section of the Aiven blog on our website, and I probably recommend having a look at that. And we also have some worked examples. Apache Kafka, as you probably guessed by the Apache part, is administrated by the Apache Software Foundation, who look after a bunch of really important open source projects ever since they shipped the Apache web server many, many years ago. They have some brilliant resources diving further into the introductory elements of Kafka in their Getting Started section. We have very recently released an MCP tools server for Aiven Kafka. So if you want to have a go at building things with Kafka on Aiven and you like using MCP, we have that there to try out. And finally, I would thoroughly recommend checking out some of the blogs and resources in the r/Apache Kafka subreddit. Not a huge fan of Reddit, but I do like the Apache Kafka Reddit, so it's worth a look. Robin and the team there are great, and they have some really good stuff. Awesome. So we have some questions in the chat. Question from Daniel. What data storage options are available on the Aiven platform, and what are the features to bear in mind when storing event stream data? Great question. So there are two main kind of modalities of Kafka cluster on Aiven. Classic Kafka, where your data is written to the local disk attached to the instance your Apache Kafka cluster is running on, or your broker is running on rather, and diskless Kafka, or tiered storage, where your data is written to a remote object store. And there are two main use cases associated with these modalities. For the first, that is the standard experience of Kafka. Your partitions are written to local disk, and they are very quick to read and write from. You get that real-timeness and that instancy of Apache Kafka. But there are costs associated with that. Because data is written to those local brokers, the data has to be replicated, those partitions have to be replicated between brokers. And if your brokers are in different cloud availability zones, which is good practice in terms of disaster recovery, like if you put all of your eggs in US East 1, you're liable to lose them. you will be charged by your cloud provider for moving that data. Which is why we also offer this other mode for Kafka, which is diskless, where your data is written to an object store instead of to local disk. Now, object store puts are slower than disk read and writes, but because your data is replicated in the object store via the object storage API, you don't need to replicate it between brokers when you rebalance or when you add and remove brokers. And in general, on produce and consume, you don't have to replicate data across partitions. So that can significantly cut down on your network costs, but it is slightly higher latency. So those are the two main options. I would say for most Kafka users, the difference in unit economics for object storage versus Classic is minimal. So you're fine using Classic. If you're using that megabyte a second to 5 megabytes a second sweet spot, stick with Classic. If you have a use case which is tolerant of higher latency, say you're doing logging or observability, you have very high data volumes, I would strongly encourage considering diskless. And that's a per topic switch that you can flick. Adds latency, up to a second of latency, but it is significantly cheaper. So it's worth considering. If you kind of sit in a sweet spot where you're not a large organization that can tolerate latency, but you're not a smaller scale org or project that is shipping small volumes of data, there are some other approaches you can consider too. You can look at tiered storage, where you write some portion of your Kafka data to object storage, either based on rules around the type of data or how long it's been stored, which can help reduce cost without impacting the latency for your real-time data as it arrives. And you can also look at some options around rack-aware partitioning, where you can ensure that data is produced to a broker which is nearer to your consumer, in the sense of being in the same data center or co-located in the cloud. So yeah, I would say the main takeaway here in terms of storage options are local, simple, fast, potentially more expensive at scale, diskless and tiered for larger data volumes that are more latency tolerant. But yeah, great question. Thanks, Daniel. With diskless topics, what happens to consumer latency and recovery when data has to come back from object storage? How does it compare with the traditional self-hosted Kafka cluster using local disks? So the most important thing here is the difference in the latency of a disk read with an IOPS operation from local NVMe, and the difference of a get operation from an object store like S3. We have done some very extensive benchmarking on this, and you can find the data on our website. If you search Aiven diskless benchmarking, we have some articles on it. Typically, the average distance is 1 second to 1.5 seconds of latency. So if you have a use case which is reliant on having your data in less than a second, you should not be using diskless. However, we found that talking to customers, most people who are doing things like logging or observability or have data going to dashboards can cope with a second of latency, in which case, that read is less of an issue. Now, when it comes to recovery, the situation's flipped entirely. As I mentioned before, rebalancing Kafka partitions can be very slow because you're having to copy between brokers. Even though reading and writing from local disk is faster, your reading and writing from remote disks for the replication partitions is slow. For very large Kafka clusters, we're talking like terabytes of data a day, your rebalance might be 6 hours. It might be days, depending on the volume of data you have to move and how fast the network connection is to your brokers. For diskless, it's effectively instant, because instead of taking a large amount of data, figuring out where it's going, and copying it between multiple brokers multiple times, diskless is zero copy. All of the data is there in object storage. And so whilst you can replicate your data across multiple buckets, there's not necessarily a need to, because most object stores have 6 nines of reliability. But even if you have it replicated across 2 buckets, you're only replicating your data once. You're not having to replicate it for each broker in the cluster every time you add or remove a node. So for day-to-day operation, Classic is faster, but for recovering from an incident, diskless is 10 times faster at least. It is exponentially faster as your data volumes increase. But yeah, great question. Awesome. Thanks everybody, and I'm going to wrap it up there because I think we're at time. But yes, if you have any more questions, please do reach out on LinkedIn. All the best, and hopefully to see you at another session soon.